Um, I think I go straight on now to looking at an example. And we're going to look at an example of building a very simple set of tests for a stack data structure. So I'm looking now directly into this slide deck here, pragmatic testing, unit test examples. This is quite a influential book on unit testing. It's the second edition of an even more famous book published quite some time ago. These authors here, Andrew Hunt and Dave Thomas, really pioneered this field. And if you're interested in looking at the origins or looking at how at least they conceived of the field, well worth looking up their writings and their blogs. This revised version has been largely rewritten by another author, but he has had the original authors on board for his evolving philosophy. So this book and a predecessor of it introduced unit testing to the community some time ago, and they introduced it using examples rather than any substantial theory. I'd like to just work through one example from that particular text here, modified it slightly. And the idea is that we're developing a stack data structure. Stack, as you all know, allows you to first in, first out, push items onto a stack, pop things off a stack, see is the stack empty, see if we can access the top of the stack without popping it. It's a fundamental data structure in computer science. Here's how we might implement it. Again, I don't propose to spend some time looking at this implementation, just noting a few features of it. We're implementing the stack using built-in arrays, and also a next index top pointer. We are creating an array of maximum 100. And then in the pop element, we are data structure. We've just introduced the stack implementation here. And now we're going to try and build up a set of tests to exercise this stack. Let's have a look at them. First of all, we introduce stack test class, and we introduce a before and an after annotation to indicate the initialization. We want to run before and after each test. Not all the tests, but each individual test. We will be creating a new stack and disposing of the stack. This ensures that each of the tests is fully isolated and won't interfere with each other. Bear that in mind, because that's quite an important principle of testing. Now, how would we go about testing it? Well, we might start just by contemplating a little bit what it is the stack is, and coming up with a set of tests, maybe just by sketching them out, that we think, if they passed, would mean our implementation was pretty robust and reliable. It's largely free-form thinking here for the moment. We will be developing later on more systematic ways of coping with a blank canvas test, if you like. Here's a very simple statement. With an empty stack, push a test string onto the stack, verify top returns that string several times in a row, and verify that it is empty returns false. So these are, I suppose, canonical expectations of a stack that we'd be used to in our understanding of it. Another example, for a brand new stack, see if is empty should return true, and also see if top and pop throw exceptions. So it's part of our understanding that if you try to pop or call top on an empty stack, it fails seriously with an exception. Again, I won't go through all of these in turn because we're going to look at each of these separately in a moment. Here's another example. Pop to remove the test string, verify the same string came off that you removed. Is empty should be true. Pop again should verify an exception is true. So what do these tests look like? Well, here's the first one. Push item 1 onto the stack, and then verify that top returns item 1 3 times in a row. So top should not only return the item1 string immediately, it should also return it on successive calls, i.e. we're quite adamant that top should not alter the stack or cause anything to be removed from it. And finally, isEmpty should be false. So we're making sure we check that here via the assert false as opposed to assert equals assertion. Seems straightforward enough. It seems obvious, in fact, but it's important incremental stability being introduced into our system by writing simple tests like this. Here's another example then. For a brand new stack, isEmpty should be true. Top and pop should throw exceptions. These are 3 separate cases we've decided to incorporate them into. Just focusing on the JUnit 4 annotations for these. This is the simple case 1. Brand new stack. Remember, we've created a stack just before this test is run, and now we're checking it's empty. Second test, calling top, we're saying should throw an exception. So we're using the annotation available in JUnit 4 to deliberately expect an annotation. And you can see on the right over here, on the left, sorry, over here, how we might be doing that if we are working in earlier version of JUnit. And finally, in case 2 below, pop also is generating an exception. Remember, an exception is an exceptional situation. It means execution of the current stack terminates and we escape out from the current current call stack to resume execution wherever the exception is caught. Here's another example then. We're popping to remove a test string, verifying it's the same string we inserted. We're then checking to see the stack is now empty. And then we're trying to pop the stack and we're verifying that an exception is thrown. The subtlety involved in this test here is that we should never execute this line. If we execute that line, we're doing an explicit fail, and fail will cause a red and a termination of this particular test immediately. Otherwise, the test should run on, and we should resume in the exception here, indicating that yes, we got the exception and the stack did behave as expected. That assert true is perhaps not needed. It's just put in there as a marker. Keeping going here with these tests, getting a bit more subtle here now. We're pushing on 3 strings. We're then popping them off one by one, and we're verifying that we got the 3 strings back. But we're not happy this time with a simple assert equals. We want an assert same. Assert same is quite subtly different from assert equals. It means that test 1, test 2, and test 3 are actually the objects we pushed on. They're not equal, they're not containing the same string, they are the same objects. That might be important in our implementation. We don't want our stack to clone or replicate the objects. We want them to hold the actual objects we've asked it to hold. This test is verifying that. So it's an important semantic exercise in our test strategy. One more example. Does it work with null? We'll have something to say about null later on. Here we've decided we do support null. So if it pushes on a null, you can get it back. And that's what we're verifying here. And lastly, can we use the stack after it has been in an error state? So here, exceptions are being thrown. We are definitely hoping that we do not get to execute this fail statement, which will terminate the test. We proceed to the exception handler, and then we proceed with the remainder of the test starting down here. Here we're just doing a push, not doing anything exciting, but we're just verifying that the stack is stable again and usable. so that exceptions aren't catastrophic if they occur. Now, one last point on this test. Now, this is a very powerful point we need to just dwell a little bit on for the moment. Very early in the slide deck, we introduced our implementation of the test stack. That is, we decided to implement the stack using an array, a built-in array. This was our system under test, and we proceeded to evolve a set of tests then to verify that, yes, this was behaving as specified. Down here, we might decide, well, let's do another implementation. And the other implementation is a complete replacement for the system under test. In particular, we've chosen to implement the stack again, this time using a stack, because of course this is a fundamental data structure already present in our library. So here we're using a stack class we have extracted from the utils library, and we're delegating all of our implementation to that stack class. So we have a new system under test, and we're using features that have already been implemented elsewhere. However, all the tests we've written should function correctly. All we need to do is replace our fixture, removing the array stack we've implemented, and create an instance of our collection stack. All our tests now that we've invested in aren't wasted. They now test does this new stack adhere precisely to the semantics we were expecting and that we already had delivered in our old stack. If they all pass without incident, then we've done a complete replacement of a subsystem with some considerable confidence that that replacement hasn't caused any knock-on or serious error conditions. So that's quite a nice and very important benefit of unit tests, the ability to evolve or substitute subsystems as needs arise, as new strategies emerge, or as different implementation concerns cause us to evolve some components. Okay, I'm going to take a little pause now to take any questions for a few moments, and I'll disconnect my mic and camera for a few seconds, and we'll come back then and we'll look at another test along the same lines. See you in a few seconds. I'll give it maybe 8 minutes or so.